Every single year, more than 300 million tons of salt are produced worldwide, with sea salt accounting for roughly 30% of that total, making it one of the most abundant harvested minerals on Earth. A single large-scale salt production facility can cover over 15,000 acres of shallow evaporation ponds, producing up to 1 million tons annually using nothing more than sunlight, wind, and seawater. These coastal operations transform ordinary ocean water containing just 3.5% salt into brilliant white crystals that eventually season food on tables across the globe. But how do producers move billions of gallons of seawater through carefully engineered pond systems that concentrate brine over months? What combination of ancient solar evaporation techniques and modern agriculture technology enables precise crystal formation and industrial-scale harvesting? And why has sea salt evolved from a basic commodity into a premium product commanding prices 50 times higher than standard table salt? Welcome to AgriCraft, where we explore the real stories behind your food. All will be revealed in this video. The story of salt production is inseparable from human civilization itself, stretching back at least 8,000 years to when Neolithic communities began boiling seawater or mining salt deposits to preserve food and enhance flavor. Ancient civilizations from China to Rome established elaborate salt production systems and trade networks, recognizing salt as so valuable that it was used as currency and sparked wars over control of production sites. The word salary itself derives from the Latin word for salt, reflecting how Roman soldiers were sometimes paid in salt rations. Sea salt specifically has been produced through solar evaporation for millennia, with evidence of salt gardens operating along Mediterranean coasts since ancient Egyptian times. The basic principle has remained remarkably consistent. Allow the sun and wind to evaporate seawater in shallow ponds until salt crystallizes and can be harvested. What has changed dramatically is the scale, efficiency, and sophistication of modern operations. Today, the global salt market is valued at approximately $14 billion annually, with sea salt representing a growing premium segment. China dominates total salt production, generating over 70 million tons per year from both sea salt operations and underground mining, followed by the United States at around 40 million tons, India at 30 million tons, and Germany at 14 million tons. The leading sea salt producers include India with extensive operations along its vast coastline, China with traditional salt fields dating back centuries now modernized with industrial equipment, and Mediterranean countries including France, Spain, Italy, and Greece, where artisan salt production has evolved into sophisticated commercial operations. The United States produces sea salt primarily in California, particularly the San Francisco Bay Area, where salt ponds have operated since the Gold Rush era, and in Hawaii, where premium finishing salts command extraordinary prices. The journey of sea salt begins not with planting seeds but with selecting optimal coastal locations that provide the essential raw material of clean seawater and the environmental conditions necessary for efficient evaporation. The site selection process evaluates multiple critical factors. First, the coastline must allow construction of large shallow ponds, either by excavating coastal land or utilizing natural tidal flats and lagoons. Second, the climate must provide abundant sunshine and steady winds to drive evaporation, ideally with low rainfall that would dilute the concentrating brine. Third, the seawater itself must be relatively clean, free from industrial pollution, sewage contamination, or excessive sediment that would compromise salt quality. The traditional sea salt producing regions share common climatic characteristics: Mediterranean climates with hot, dry summers, subtropical regions with distinct dry seasons, or arid coastal zones, where evaporation far exceeds precipitation. Environmental requirements for sea salt production are surprisingly specific. The annual evaporation rate must significantly exceed the rainfall rate, ideally by a factor of 5 to 10 times or more. Regions receiving less than 20 inches of rainfall annually while experiencing over 100 inches of evaporation potential are ideal. Temperature matters because warmer water holds less dissolved oxygen and evaporates faster, with optimal air temperatures ranging from 75 to 95 degrees during the production season. Wind speed and consistency are crucial as moving air carries away water vapor, preventing the air immediately above the brine from becoming saturated and slowing evaporation. Coastal areas with steady afternoon sea breezes provide natural advantages. The topography should be relatively flat to allow construction of large, shallow ponds with minimal excavation. Soil composition matters as well, with clay or naturally impermeable substrates preferred to prevent brine from seeping into groundwater. The cultivation of sea salt, though it seems strange to use agricultural terminology for mineral production, shares remarkable similarities with farming. Just as farmers prepare fields for planting, salt producers carefully prepare and maintain their evaporation ponds. The pond systems typically consist of multiple stages spread across vast areas. The first stage involves large concentrator ponds where incoming seawater begins its evaporation journey. These ponds may be several feet deep initially and cover hundreds of acres. Seawater is pumped or flows naturally from the ocean into these ponds where solar radiation and wind begin reducing water volume. As water evaporates, the salinity gradually increases from the initial 3.5% to 6%, then 10%, and eventually to 25% or higher over the course of weeks or months. The seawater intake systems range from simple gravity-fed channels that fill ponds during high tides to sophisticated pumping stations using industrial machines to move millions of gallons daily. Many operations use gates and channels that can be opened to allow tidal flooding, taking advantage of natural ocean cycles rather than requiring continuous pumping. The intake structures include screening systems that filter out debris, seaweed, and marine organisms that could decompose in the ponds and contaminate the salt. Some facilities employ settling ponds where suspended sediments fall out before brine enters the main evaporation system. As the brine concentrates, it flows through a series of increasingly shallow ponds. This stage system is engineered based on precise understanding of how different minerals crystallize at different salinity levels. Early in the concentration process, calcium carbonate precipitates out, forming a white coating on pond bottoms. As salinity increases further, calcium sulfate or gypsum begins crystallizing. These early precipitates are considered impurities in salt production, so the brine is moved to new ponds before the primary salt crystallization begins. Only when the brine reaches approximately 25 to 28% salinity, nearly 10 times more concentrated than seawater, is it transferred to the final crystallizing ponds where sodium chloride will form. The crystallizing ponds or crystallizers are the heart of the operation. These are extremely shallow, typically just 6 to 12 inches deep, covering hundreds or thousands of acres in large facilities. The shallowness is critical because it maximizes the surface area to volume ratio, dramatically accelerating evaporation. The pond bottoms are carefully prepared with clay liners or compacted salt layers from previous harvests that create smooth, impermeable surfaces. As the brine sits in these shallow crystallizers under intense sun and wind, the water continues evaporating and eventually supersaturation occurs. At this magic threshold, sodium chloride molecules begin organizing into cubic crystal structures, forming initially as tiny seed crystals that grow larger over days and weeks. The crystal growth phase requires careful monitoring and management. The ideal conditions produce large, uniform crystals that are easier to harvest and process. If evaporation happens too rapidly, many small seed crystals form simultaneously, creating fine salt that is harder to handle. If evaporation is too slow or interrupted by rainfall, crystal growth is uneven. Skilled salt farmers monitor weather forecasts closely, managing brine levels and timing harvest to avoid rain events that could dissolve developing crystals. The crystallizers are typically managed in rotation, with different sections at various stages of crystal development to enable continuous harvesting rather than a single annual harvest. The cultivation period from initial seawater intake to harvestable salt crystals varies dramatically with climate and season. In optimal Mediterranean or subtropical conditions, the complete cycle might take 3 to 6 months. In less ideal conditions or during cooler seasons, it can extend to 8 or 12 months. Some operations in extremely hot, arid climates can complete cycles in as little as 6 to 8 weeks. This variability means that salt production is inherently seasonal in many locations, with harvest concentrated in late summer and fall after months of evaporation through the hottest, driest period. Throughout the evaporation process, pond maintenance is constant. Workers inspect levees and dikes that separate ponds, repairing any erosion or animal damage. They monitor water levels and adjust flow between ponds. They watch for algae blooms that can discolor salt or create off flavors. Some operations intentionally cultivate specific halophilic organisms, salt-loving microorganisms and algae that give salt distinctive colors and flavors prized in gourmet markets. The famous fleur de sel from France develops its delicate flavor partly from microorganisms in the brine, and Hawaiian pink salt gets its color from trace minerals and specific algae. However, most commercial operations aim for pure white salt and work to minimize biological activity in their ponds. Harvest timing is determined by crystal size and layer thickness. When the salt layer at the bottom of crystallizers reaches sufficient depth, typically 2 to 6 inches, and the crystals have grown to desired size, usually ranging from fine granules to chunky flakes, the harvest can begin. Traditional harvesting methods, still used in small artisan operations and for premium products, involve hand raking. Workers wade into drained or very shallow ponds using wooden rakes or scrapers to gather salt into piles that are then shoveled into baskets or wheelbarrows. This manual approach is labor-intensive but allows careful selection of the best crystals and minimal contamination. The most prized salt is sometimes the thin crust that forms on the brine surface, harvested by skimming with special sieves before it sinks. This fleur de sel, or flower of salt, commands premium prices due to its delicate texture and hand-harvested nature. Modern industrial-scale operations have mechanized harvesting using specialized equipment adapted from agriculture technology. Salt harvesters resemble small agricultural machinery but are built to withstand the corrosive salt environment. These machines may use rotating scrapers or plows that push salt into windrows, similar to hay raking. Other designs employ conveyor systems that lift salt from pond floors directly into collection bins or trucks. The largest operations use enormous self-propelled harvesters that simultaneously cut, lift, and load salt in continuous operations capable of harvesting hundreds of tons per day. These industrial machines must be constructed from or coated with corrosion-resistant materials like stainless steel or special polymers, because ordinary steel would corrode rapidly in the salt environment. After mechanical harvesting gathers the salt into piles, front-end loaders and dump trucks transport it from the ponds to processing areas. The wet salt, still containing residual brine and moisture, is piled in massive mounds that may be several stories tall and contain thousands of tons. These stockpiles allow drainage and initial drying before further processing. Rain can be a concern at this stage, potentially dissolving salt or introducing impurities, so some operations cover stockpiles with tarps or store them in open-sided sheds that protect from precipitation while allowing airflow. Transportation to processing plants happens via internal haul roads within the salt works or by short-distance trucking to nearby facilities. The processing plant is where raw harvested salt transforms into the finished products consumers purchase. The first processing step involves washing to remove adherent clay, gypsum, or other impurities. This might seem counterintuitive to wash salt, but the washing uses saturated brine rather than fresh water, so the salt does not dissolve. The saturated brine, already holding as much salt as water can dissolve, washes away surface contaminants without affecting the salt crystals themselves. Industrial washing systems use rotating drums or vibrating screens through which saturated brine flows, agitating the salt and carrying away impurities in the overflow brine. After washing, the salt enters drying systems. Even though it was formed through evaporation, the harvested salt still contains significant moisture, perhaps 10 to 15% by weight, mostly as brine films on crystal surfaces and trapped in the crystalline structure. Drying is essential for storage, stability, and to prevent caking. Industrial dryers vary by facility but typically involve rotating drums through which hot air flows, tumbling the salt while evaporating moisture. Other designs use fluidized-bed dryers where air blows up through a perforated floor, suspending and drying salt particles simultaneously. The drying temperature must be controlled carefully, usually between 200 and 400 degrees, hot enough to drive off moisture efficiently but not so hot as to cause undesirable changes in crystal structure. For premium finishing salts marketed on their specific crystal shapes and textures, gentle drying at lower temperatures preserves the desired characteristics. Screening and grading happen after drying, using vibrating screens with precisely sized mesh openings that separate salt into different size fractions. Fine salt passing through small mesh is collected for table salt or food processing applications. Medium crystals are gathered for all-purpose cooking salt. Large flakes or chunks are kept separate for finishing salts or specialty applications. This sorting process may involve multiple stages with progressively finer screens, creating a range of products from a single harvest. Automated systems use conveyor belts to move salt through the screening equipment and distribute different grades to separate collection points. Quality control throughout processing is essential, even for a product as simple as salt. Laboratory testing confirms that sodium chloride content meets specifications, typically 97 to 99% or higher depending on grade. The remaining small percentage consists of trace minerals, primarily magnesium, calcium, potassium, and sulfate compounds that are natural components of seawater. Some producers emphasize these trace minerals as beneficial, marketing sea salt as more natural and nutritious than highly purified table salt. Testing also checks for heavy metals, microplastics, and other potential contaminants that are unfortunately increasingly present in ocean waters. Moisture content is verified to ensure proper drying. Physical characteristics, including crystal size distribution, color, and caking tendency, are evaluated. Only salt meeting all quality standards proceeds to packaging. Some salt undergoes additional processing steps depending on intended use. Table salt is typically ground into fine powder using industrial mills, then mixed with anti-caking agents like calcium silicate or sodium ferrocyanide that prevent clumping in humid conditions. Iodine is added to create iodized salt, a public health intervention that has virtually eliminated iodine deficiency disorders in countries with fortification programs. The iodine is mixed in as potassium iodide or iodate in carefully controlled amounts to provide recommended dietary levels. Salt destined for food processing or industrial applications may be compacted into pellets or evaporated into granules with specific size and density characteristics suited to automated dosing equipment in factories. Packaging varies enormously depending on market segment. Consumer table salt is filled into small containers ranging from shakers to boxes to canisters, using automated packaging systems that weigh precise amounts, fill containers, seal them, and apply labels in continuous high-speed operations. These automated systems can package hundreds of units per minute, with quality control checkweighers ensuring each package meets target weight. Premium finishing salts are often packaged in smaller quantities with elaborate packaging that emphasizes artisan production, distinctive characteristics, and culinary applications. Some are packaged in ceramic or wooden containers that reinforce premium positioning. Food industry salt is packaged in large bags weighing 50 to 100 pounds, stacked on pallets for efficient handling. Water softening salt for residential and commercial use is sold in bags or pellets. Industrial salt for chemical manufacturing or de-icing moves in bulk, loaded directly into rail cars or trucks that transport it without further packaging. Labeling meets regulatory requirements while also serving marketing purposes. Consumer packages include nutrition facts panels, though salt has a simple composition with sodium being the primary nutrient of concern. Labels identify country of origin, which is important in premium segments where consumers pay extra for salt from specific famous regions. Certifications may include organic status, which seems odd for a mineral but relates to production methods and absence of additives, or kosher certification important to observant Jewish consumers. Many artisan salt producers tell stories on their labels about the specific salt marsh or sea where their salt originated, the production methods used, and suggested culinary applications. Storage of packaged salt before distribution is straightforward because salt is one of the most stable food products, essentially imperishable if kept dry. Warehouses storing salt need not be climate controlled, though they should provide protection from rain and excessive humidity that could cause caking even in packaged salt. The palletized packages are stacked in systematic arrangements that allow efficient retrieval and shipment. Inventory management follows standard distribution practices with computerized systems tracking stock levels, lot numbers, and shipping schedules. Distribution channels for sea salt span from local to global. Commodity salt moves through conventional food distribution networks, from processing plants to regional distribution centers operated by food service companies or retail chains, then to restaurants, institutions, and grocery stores. The logistics are efficient but unremarkable, with salt traveling in the same trucks as other shelf-stable foods. Premium artisan sea salt follows different channels, often sold through specialty food distributors who serve gourmet stores and high-end restaurants, or through direct channels including website sales where consumers order directly from producers. The direct model allows small producers to capture full retail margins and build brands around their stories and unique product characteristics. Export markets are significant for countries with favorable salt production conditions. France exports premium sea salt globally, with Gironde salt from Brittany being world famous. Mediterranean countries including Greece, Spain, and Portugal export both commodity and specialty sea salt. Hawaiian sea salt, despite Hawaii being a U.S. state, is treated almost like an imported luxury in mainland markets due to its distinctive characteristics and limited production. Import regulations are generally minimal for salt as it poses little food safety risk, though documentation confirming food-grade quality and origin is required. Pricing reflects the enormous range from commodity to luxury product. Industrial-grade salt might wholesale for $30 to $50 per ton, translating to mere pennies per pound, making it one of the cheapest minerals in commerce. Food-grade sea salt for general use wholesales from $100 to $300 per ton, or 5 to 15 cents per pound, with retail prices perhaps double that. Premium finishing salts command $1 to $3 per ounce, or $16 to $50 per pound, a thousand-fold price premium over commodity salt justified by distinctive characteristics. Hand harvesting, limited production, and marketing. The most exclusive salts, including certain Hawaiian varieties, Japanese sea salts, or limited production artisan salts, can exceed $100 per pound. Byproducts from sea salt production are modest but valuable. The mother liquor or bitterns remaining after salt crystallization is extremely concentrated in magnesium, potassium, and other minerals. These bitterns are sold to chemical companies that extract magnesium compounds used in agriculture, pharmaceuticals, and industrial processes. Some salt operations harvest gypsum that precipitates in early evaporation stages, selling it for use in drywall manufacturing, cement production, or agricultural soil amendments. The least desirable materials, including bottom mud and organic matter cleaned from ponds, are usually disposed of or in some cases used as fill material for construction projects. Culinary applications of sea salt are virtually unlimited given that salt is the most universal seasoning. Beyond simply salting food during cooking, sea salt plays specific culinary roles. Finishing salts are sprinkled on completed dishes just before serving, providing bursts of salty flavor and interesting texture from the coarse crystals. Chefs use different sea salts for different applications based on crystal size, color, and subtle flavor notes. Bakers use sea salt in bread and pastries where its clean flavor and lack of additives compared to iodized table salt are preferred. Salt for preserving, whether for pickling, curing meat, or fermenting vegetables, often specifies pure sea salt without anti-caking agents that could interfere with fermentation. The diversity of sea salts from around the world has created a culture of salt connoisseurship, with enthusiasts collecting and comparing salts from different origins, much like wine enthusiasts explore different regions. Nutritional value of sea salt is essentially sodium chloride, the chemical compound providing saltiness. The trace minerals present in unrefined sea salt, perhaps 1 to 3% of total content, include magnesium, calcium, potassium, iron, zinc, and others. Marketing often emphasizes these minerals as health benefits, though the amounts are so small that sea salt cannot meaningfully contribute to mineral nutrition. A person would need to consume dangerous quantities of sodium to obtain significant mineral nutrition from salt. The more legitimate nutritional consideration is sodium intake itself. Health authorities recommend limiting sodium consumption to reduce risks of high blood pressure and cardiovascular disease, with recommended limits around 2,300 milligrams per day. equivalent to about 1 teaspoon of salt. Whether that sodium comes from sea salt or table salt makes essentially no difference physiologically, though many people prefer the taste of sea salt. Environmental considerations in sea salt production involve both impacts and benefits. The creation of evaporation ponds transforms coastal landscapes, potentially destroying natural wetlands or beaches. However, once established, salt ponds can provide habitat for specialized birds, fish, and invertebrates adapted to hypersaline conditions. Some salt works have become important refuges for migratory shorebirds that feed on brine, shrimp, and other organisms thriving in the ponds. The concentrated brine discharged when ponds are drained poses disposal challenges as it is denser than seawater and can create dead zones in receiving waters if not diluted properly. Some operations recycle brine continuously rather than discharging it. Solar evaporation itself is arguably the most environmentally friendly method of salt production, using renewable solar energy rather than burning fossil fuels to boil brine as vacuum salt production does. Water consumption is effectively zero, as seawater is the input and evaporation returns water to the atmosphere where it eventually returns as precipitation. The climate impact is minimal compared to industrial salt production methods. Sustainability in sea salt production centers on maintaining clean ocean water sources and protecting coastal environments that make production possible. Producers have vested interests in preventing ocean pollution and coastal development that could contaminate seawater or eliminate production areas. Some salt works actively participate in coastal conservation, recognizing that their business depends on healthy marine ecosystems. The artisan salt movement emphasizes small-scale production with minimal environmental footprint, hand harvesting that employs local workers, and preservation of traditional knowledge and techniques that might otherwise be lost to industrialization. Looking at the journey from seawater pumped into vast shallow ponds through months of solar concentration as water evaporates and salinity increases, to the magic moment when crystals form in shallow crystallizers, then through mechanical harvest using adapted agricultural equipment, transportation to processing plants where washing and drying prepare the salt, screening that grades it by size, and packaging that protects it during distribution to markets ranging from local grocery stores to international gourmet shops. The sea salt supply chain reveals a mature industry, balancing ancient practices with modern efficiency. The 300 million tons of salt produced globally each year include the 90 million tons of sea salt generated through solar evaporation, representing one of humanity's oldest extraction industries still thriving in the modern economy. From the extensive salt works of India, producing millions of tons annually, to the small artisan paludiers in France hand-harvesting fleur de sel 1 pound at a time, the range of production scales and methods encompasses everything from commodity chemicals to culinary luxuries. American operations from the industrial salt ponds of San Francisco Bay to the premium Hawaiian salts marketed worldwide participate in this global industry while maintaining distinctive regional characters. The combination of natural processes where solar energy and wind provide the power for transformation with human ingenuity, designing efficient pond systems and developing mechanical harvesting technologies creates a production model that remains economically viable and environmentally sustainable. As consumers increasingly seek products with stories connecting them to specific places and traditional practices, sea salt from recognizable origins with transparent production methods appeals to values beyond mere function, transforming a simple commodity into a premium food item that brings the ocean to the table. Thank you for watching this exploration of sea salt production here on AgriCraft. If you found this journey from ocean water to finished salt informative, please hit the like button and subscribe to our channel for more deep dives into food production and agriculture technology. Leave a comment below telling us about your favorite sea salt or questions about solar evaporation and coastal salt farming. Until next time, keep exploring the remarkable processes behind the foods we often take for granted.